Yes, students, welcome back to the discussion of backpropagation algorithm, which we have left partial in the last class. Keep marking your attendance, don't forget. Okay, we understood here in the previous class how complex networks can be built by using these perceptrons. Multi-layer networks can be built in order to do some complex processing of information, like in speech recognition or image processing. We can build multiple layer networks by using these perceptrons. And we have seen how to smooth the function, that is the perceptron rule, so that the threshold will lie between 0 and 1 by using sigmoid function. Sigmoid function is the alternative for us in order to smooth the discontinuous threshold that we have in perceptron. That is represented by a symbol like this. Okay, this is a graph which represents the sigmoid unit. It lies between 0 and 1. The range of values of this sigmoid unit lies between 0 and 1. This is how we can smooth the perceptron's output. For that, we have seen this layer is the perceptron, which will further be given as, and that layer's output is further given as input to the sigmoid unit. The perceptron layer will create a linear combination of all the elements, W1, X1, W2, X2, and so on. Now that linear equation is further given to sigmoid unit so that it will be brought into the range, the output will be brought into the range of 0 and 1 by using the representation 1 by 1 plus e power minus x. Okay, this sigmoid unit is also called as logistic function because we are applying log and bringing it to the limit of 0 and 1. Right? You don't have log for negative values. So that indicates it is a logistic function. Okay, now let us see step by step of this backpropagation algorithm. In this backpropagation algorithm, see what is the input, the training examples. In order to train the neural network, new, the learning rate, see this is new. That is the learning rate. Learning rate is with what adjustment it should go or proceed forward, with what rate it should adjust the weight to proceed forward to a global minimum. Okay, initially the adjustments can be larger, but as it comes towards a global minimum, towards reducing the prediction error, that learning rate have to be smaller and smaller so that it doesn't miss the global minimum. And once the global minimum is reached, this learning rate will completely decay because prediction error is no longer encountered. When there is no prediction error, the algorithm can stop learning, right? So the learning rate will become 0. And what is the next term? N in. N in indicates the number of input nodes, and N out indicates the number of output nodes. Okay, something like neurons. Each node denotes a neuron in the neural network, and N hidden is the number of hidden layers. So what is the input given to backpropagation algorithm? What is the data on which this backpropagation algorithm works? Set of training examples, the learning rate with which it has to learn to reduce the prediction error, and number of input layers, number of output layers, and the number of hidden layers. Okay. Now each training example is a pair of the form x bar, x vector, and t. What is x vector? It is combination of lots of input attributes, right? x1, x2, x3, and so on. And t, sometimes you may get single output, single target value. Sometimes you may get multiple target values. Remember, neural networks doesn't give only one single output. You can model the architecture to give one single output, but still it is capable of giving multiple outputs, right? In that case, the target value will not be single. It will be multiple. If the output layer has multiple nodes, then it has multiple outputs, right? So the targets also can be taken as a vector here. Vector is collection of elements, similar elements. Now this target vector T bar is nothing but T1, T2, T3 if it has three outputs. If the neural network has three outputs, then the target vector is a collection of all these three outputs, T1, T2 and T3. Okay, three target labels are given for this particular training example. Okay, I'm talking about the real life scenario where you may come across multiple outputs, not single output. In that case, target has to be represented as T vector, not as simple T. Okay, where X bar is the vector of network values and T bar is the vector of target network output values. Okay, I said if it is if there are multiple outputs, then you get as target vector. Okay, now N new is the learning rate, this line. New is the learning rate. Initially, you can fix it around 0.05. Then you can reduce it to 0.005 and further reduce it to 0.00001. And slowly it will start decaying when the weight adjustments converge. Means no longer the weight adjustments need to take place. Why? Because the prediction error has reached its minimum. So no longer the model has to learn anything. In that case, the learning rate will completely diminish or completely vanish, that it becomes zero. Okay, so new is the learning rate, n in is the number of network inputs, n hidden is the number of units in the hidden layer, and n out the number of output units. Okay, now the input from unit I to unit j is denoted as xji. Do not get confused. If you want to represent the input from unit I, see this corner, to unit j, then you represent this as x of ji, not x of ij. Okay, so don't think it as printing mistake. You have to represent like this. So wherever the tail ends, this is the input from unit I to unit j. Wherever the tail ends, that has to be denoted first. Okay, so it is xji. The input from unit I into unit j is denoted as xji, and the weight from unit I to unit j is denoted as wji. Okay, till here it is clear. Backpropagation algorithm takes set of training examples, the learning rate that you fix, the number of input units, number of output units, and the number of units in the hidden layer or number of hidden layers. Okay, now create a feed forward network. Feed forward network means from one layer it is feeding input to the next layer. That layer again gives output which is fed as input to the next layer, maybe output layer or another hidden layer. Okay, so that is called as feed forward network. Create a feed forward network with n input, n number of inputs, n number of hidden units, and n number of outputs. Okay, so I have the structure like this. Say these are my inputs, these are my first hidden layer, this is my first hidden layer, this is my second hidden layer, and finally it will give some output. Right, this is how we construct a neural network. Means you're giving the structure to the model and the model will learn based on that structure. Okay, now initialize all network weights to small random numbers. Be it a neural network or any other algorithm, how it starts with random weights because it doesn't know what would be the best selection of the weights in order to make the prediction error as low as possible. In that case, it has to take some random weights in the beginning. Now, based on how much prediction error it encounters, weights will be adjusted. Okay, now with this particular set of weights, the prediction error is very high. Now adjust the weights and check. Yeah, the prediction error reduced. Again adjust the weights. The prediction error reduced still more. Again adjust the weights. The prediction error reached its minimum value. So that will be your global minimum. Most optimal solution. Most optimal set of weights. Okay. So initialize all network weights in the beginning to small random numbers. Say it may be between minus 0.5 to plus 0.5. Any 0.05. Okay, minus 0.05 to plus 0.05. Anywhere between them, you can start off with some random weights. Now, until the termination condition is met, what is the termination condition? There are lots of choices in choosing the termination condition also. I'll show you how you can make a choice of that. Because it should not lead to overfitting or it should not lead to more prediction error. You should find some termination condition which reduces your prediction error to the minimum and also which will not overfit your data. Okay, so until the termination condition is met, do what has to be repeated? See carefully. For each training example, X vector, T vector, in the training examples, do this. What? First case is propagate the input forward through the network. It is very simple. This algorithm is very simple. And this is compulsory question, right? So you have to remember this. Even luckily, not too much mathematics is involved in this. Okay, just focus on what steps we are taking to proceed. Initially, for each of the training examples, what you have to do? Propagate the input, means all the attribute values, forward through the network. Okay, to the next layer. Next hidden layer, which has lots of neurons. Now input the instance X bar, say first training example you have taken to the network and compute the output OU of every unit U in the network. Okay, as I said, this may be one unit, this may be one unit. You may have multiple units in your output layer. That is why you're not calculating just a single O. Like in your previous algorithms, you're not calculating a single, you're not predicting a single output. You're predicting multiple outputs. That is why you're denoting it with U. OU. OU means output at every unit U. Okay, it may be first unit, U will be 1, second unit, U will be 2, third unit, U will be 3, like that. Input the instance X bar, X vector to the network and compute the output OU of every unit U in the network. Okay, what you're doing initially is you're taking the training examples attributes. X1, in each training example, you have some attributes, say weather condition, sky condition, breeze, humidity, outlook. All these are attributes, right? Take all those input values for the training example, for each training example, feed them to the hidden input layer, which will further feed it to the hidden layer, which will further feed it to the output layer, and you get the output OU. Got it? Now, what is the next case? Propagate the errors backward through the network. That is why we call it as backpropagation algorithm. In feed-forward networks, you're feeding input to the next layers to get the final output. But in backpropagation algorithm, what is its efficiency? Where does its efficiency lie? Its efficiency lies in learning from the errors. By backpropagating the errors. Say if there are any errors in the predictions made by the output layers, that error is fed along with the inputs for the next iteration. That will make it correct the prediction errors properly by adjusting its weights. By seeing the prediction error, the network will learn to adjust its weights in order to reduce the prediction error. Okay. So propagate the errors backward through the network. The first step is propagate the input forward through the network. Once predictions are made by the output layer, what is your next step? Propagate the errors backward through the network again. Now, in that, what are the sub-steps? For each network output unit K, for each network output unit K, means you're counting the number of output layers, output units with K. If you have three output units, K will have the values 1 to 3, like that. For each network output unit K, calculate its error term sigma K. Delta K. Here we are just denoting it as delta K by using this term delta. This is also called as delta, but in order to just show you the difference between the changes. Here this delta is the change you make to the weights, to adjust the weights. Here this delta we are using for calculating the error term for each of the output units. Okay, do not get confused. This delta is for weight adjustment. This delta we are using here for just calculating the error term. Okay, for each network output unit K, calculate its error term delta K. Okay, how do you calculate that? Such that delta K is calculated as, what is the prediction error at layer K? Normal prediction error is calculated as difference between the target and the output prediction. But in this case, this prediction error happens for each of the output unit, denoted by K. That is why we are using, instead of T minus O, we are using Tk minus Ok. And for this you are applying derivation, which will give you the term that is not shown here, because that will make the algorithm complex, which will give you OK. With respect to Tk, you will make the derivation, right? So it is you will make the derivation with respect to Tk and with respect to OK also. In that case, what you will get, when you are deriving it with respect to Tk, you will get OK. When you are differentiating, when you're differentiating, not derivation, when you're differentiating it with respect to Tk, this term, the term Tk minus Ok, when you're differentiating it with respect to Tk, you'll get Ok. And when you're differentiating it with respect to Ok, you'll get Tk, right? So it is Ok into 1 minus Ok multiplied by the original term Tk minus Ok. Right? This is how you calculate the error term associated with each of the output unit K. Now what is the next step? For each hidden unit H, calculate its term delta H. Now did you notice one thing? Whatever is given in the hidden layer, this part, see this part, what is given as output of the hidden layer is not your final prediction. That is further given as input to the output layer, and output layer will give you the actual prediction. So you can't measure any error that is associated with the hidden layer, but you can measure the effect of that particular weight used in the hidden layer in terms of the prediction error of the output layer. Means you use some weights in the hidden layer, right? Now that what is the effect of the weights used in hidden layer can be studied from the prediction error of the output layer. I'm repeating again, do not get confused. Say, look at the top of the slide. These are your input layers. Now you give them as input to hidden layers. Now this hidden layer has two layers again, like this. Now this will further give input to output layers, which will give you the final prediction. This is your prediction. Now If there is any error associated with the output of hidden layer, you can't study about that. But any error associated with the output layer's output, yes, you can study that prediction error. But if you want to know the effect of weights used in hidden layer in the prediction error of the output layer, that is possible, though you can't measure the errors directly in the prediction layer. I'm trying to say you use some weights in the hidden layer, right? That weights will have influence on the prediction error of the output layer, correct? That you can notice, but you can't notice what is the error made by the hidden layer directly, because you don't have any control on the input of the output of the hidden layer, because that is given as input to the output layer. Are you following? Hidden layer doesn't give direct outputs. That is why you can't find any error associated with the hidden layer. But it has some impact on the prediction error of the output layer. That impact can be studied with respect to the weights used in the hidden layer. That is what I'm trying to tell. Is it clear, students? Now come to the third step here in the algorithm. For each hidden unit H, calculate its error term delta H. How do you calculate that? Delta H is calculated as similar to the previous step. Output prediction for that hidden layer unit into 1 minus the output prediction with that hidden layer OH multiplied by summing up all the output layers weights along with their error terms, along with their prediction errors. What is this K? The number of the output unit. What is this H? The number of the hidden unit. Okay, for each hidden unit that is associated with the output unit K, you take the weight that is used, multiply it with the error in that output unit delta K. Add up all those weights and associated errors. That will help you to study the effect of weights in the hidden layer that are used in the hidden layer, what effect they have on the prediction error that is given by the output layer. Got it? Now update each network weight WJI. WJI means when some weight is used to release some output from I to J. What is the weight used? Update each network weight WJI as, this is your learning rule, right? A weight adjustment rule. What is it? WJI equal to WJI plus some change, some adjustment that has to be done to WJI. Where, how is delta JI calculated? Delta WJI calculated? You know this already in the beginning. Nu, the learning rate, and initially we have T minus O. But this error is represented by delta here. That is why you are using delta. J is the unit number, output unit's number. If it is first output unit, delta 1. If it is second output unit, delta 2. Like that. Delta represents here the prediction error, the error term, multiplied by xji, the input term from I to j, from unit I to unit j. That is how you calculate this delta change that has to be made to the weights in order to reduce the prediction error of that particular unit. Either it is K or either it is 1 or 2 or 3 denoted by K. Right? Now the algorithm as described here applies to layered feed-forward networks containing 2 layers of sigmoid units. What are these two sigmoid layers or sigmoid units? First hidden layer and the second hidden layer. First hidden layer is first sigmoid unit. Second hidden layer is your second sigmoid unit, with units at each layer connected to all units from the preceding layer. Right? Every next layer will get the inputs from the previous layer, and this layer will further give outputs which can be fed as inputs to the next hidden layer, and that hidden layer will give output which can be fed as input to the output layer. That output layer will give you final predictions. Okay, say these are the input units. These will you feed your input to these input units, and these will give outputs to the hidden layer, inputs to the hidden layer, and these will give outputs to the next hidden layer, and these hidden layers will give inputs, their outputs as inputs to the output layer, and that will further give you the final prediction. Okay, this is how neural network works. This is the incremental or stochastic gradient descent version of backpropagation. Right? At each iteration, the error term is calculated, and accordingly, it is passed back in order to adjust the weights. It is back propagated in order to adjust the weights. The error at each iteration is back propagated in order to adjust the weights, in order to learn from the prediction errors and adjust the weights. That is why it is called as back propagation algorithm. This is the incremental or stochastic gradient descent version of backpropagation. It is learning. It is trying to descend the gradient of error by learning from the prediction errors in its previous iteration. That is why it is called as backpropagation. The algorithm updates weights incrementally following the presentation of each training example. Okay, how is the training example presented to the network layer? Following that, the algorithm updates the weights incrementally at each iteration. Now, this corresponds to a stochastic approximation to gradient descent, correct? In stochastic approximation to gradient descent, what will happen? At each iteration, every training example's error is taken and weights are adjusted. Here also it is doing the same thing. But if you want to obtain the true gradient of E, original gradient of E, one would sum the entire delta J xji, that is the error term associated with all the output units, all the output values over all training examples before altering the weight values. It doesn't check for each training example what is the error. It will first train and predict for all the training examples, calculates the overall error measure, and then the weight adjustment is done. That is called as gradient descent. But in stochastic approximation, every training example's error measure is considered. Now, the notation used here is the same as that used in earlier sections with the following extensions. What extensions we have added in this backpropagation algorithm? An index, that is an integer, is assigned to each node in the network, where a node is either an input to the network or the output of some unit in the network. It may be hidden layer 1, hidden layer 2, or output layer. That is why we are calling it as some unit in the network. Okay, an index is assigned to each node in the network. Index value I, J, K, H, all these we are using index values here, where a node is either an input to the network, it may be an input to the network, or the output of some network or some unit in the network. Now xji denotes the input from node I to unit J, and wji denotes the corresponding weight with that xji. What is delta n? Delta n denotes the error term associated with the unit n. N may be the number of that unit. It plays a role analogous to the quantity T minus O in our earlier discussion in the delta training rule. This is what I elaborated, right, while discussing the backpropagation algorithm. Instead of the prediction error T minus O, we are just using delta, that's all. Why? Because we are dealing with multiple layers. When we are dealing with multiple layers, let us choose some precise or more brief term. Okay, so that if you say delta K, it is error associated with that particular output unit K, right? Now notice the algorithm begins by constructing a network with the desired number of hidden and output units and initializing all network weights to some small random values. These are the two initial steps in the backpropagation algorithm. Now given this fixed network structure, the main loop of the algorithm then repeatedly iterates over the training examples. It repeatedly iterates over the training examples, find out the prediction error, adjust the weights, again iterate over the training examples, find out the error, adjust the weights, and so on. This is an iterative process. For each training example, it applies the network to the example, calculates the error of the network output for that particular training example, computes the gradient with respect to the error on this example. This is your target value on this particular training example. But this is a prediction made. What is the difference? That is calculated in one iteration on one training example. Then updates all weights in the network according to that prediction error obtained to reduce that prediction error. Okay, that is how weight adjustment is done. Now this gradient descent step is iterated until the network performs acceptably well. How long this gradient descent step will be performed? How long these iterations will take place? Until the network performs acceptably well, means until till the prediction error becomes minimum, till no more weight adjustments have to be done, till the network performs acceptably well. That is what we mean by acceptably well. The prediction error should be as much less as possible. Now the weight update loop in backpropagation may be iterated thousands of times in a typical application. We can't say that for one training example, this backpropagation algorithm iterates for only once. We can't say that. Until it reduces the error on that particular training example, it will keep on iterating in order to update the weights. So the weight update loop in this backpropagation may be iterated even thousands of times in a typical application like image processing or speech recognition in order to make it more perfect, in order to reduce the prediction error. A variety of termination conditions can be used to halt the processor. Now, sometimes it may go into infinite loop if, say, the image is not very clear. It may not be able to learn from that image properly. In that case, it may go into infinite loop, trying to learn from each and every pixel of the photograph. In that case, you can't wait indefinitely, right? In order to make the algorithm finish its learning. So what do? What are the termination conditions which can be used to halt the processor of this weight adjustment? Halt after a fixed number of iterations through the loop. You can fix a threshold. After these many loops, stop learning, stop adjusting the weights, because that much learning may be sufficient in order to make good enough predictions. Stop at some number of iterations, or once the error on the training examples falls below some threshold. Okay, error up to 5% is accepted. Now you are trying to reduce the error from 80%, 70%, 60%, 50%, 10%, 5%. Error is being encountered. Okay, now below this 5% error, it is acceptable, let it be. You can stop the training, you can stop the weight adjustment. Or once the error on a separate validation set of examples meets some criterion. I said, I already told you that whenever you have some data set, we divide into training set and validation set. Now you train the model on the training set and see how it performs on the validation set. Now once the error on a separate validation set of examples meets some criterion, say only 4% or 5% error, yeah, you can compromise with that kind of error. So there you can stop the training. There you can stop this weight adjustment loop, right? So the choice of termination criterion is an important one because too few iterations can fail to reduce the error sufficiently. If at all you stop with very less number of iterations, then it can't learn better. If it doesn't learn better, it can't reduce the error in the predictions. So the error will be more if there are very less number of iterations to adjust the weights. So the choice of termination criterion is very important here. You should be very careful while making this choice of the termination criterion because very few iterations can fail to reduce the error sufficiently. Prediction error may be too high if you use very less number of iterations to adjust the weights. Or if there are too many iterations, what will happen? It can lead to overfitting the training data. It will learn too much from the data. When it learns too much from the data, it can't generalize well to the unseen data. It can't generalize well with the new data. That is again overperformance of your model, which actually doesn't perform well with the unseen data. That is why you have to choose this criterion where to stop this weight adjustment loop. Okay, so that you won't end up with more errors or you won't end up with overfitting of the training data. And two more concepts we have, very simple concepts. I think within 10 minutes we can complete that. That is our 7th lecture. Let me share that. Okay, this is our last lecture under this module, where we are going to see how to add momentum term to the backpropagation algorithm and learning in arbitrary acyclic networks. Now, because of this backpropagation, say you have lots of inputs, you give them as outputs to hidden layer and they further work on that, process that information and give the outputs to the output layer, and finally you'll get the output. Right now this output has some prediction error that will be fed back to the input layers again. There is a cycle. Did you see? There is a cycle here. This is called as cyclic network. But if you want to design an acyclic network, means feed forward network, you don't want to feed anything backwards again. In that case, how learning in arbitrary acyclic networks is done, that also we are going to see today. Now, how to add momentum term? Why is it actually required? Backpropagation is a widely used algorithm and many variations have been developed for this backpropagation algorithm. But the most common is to alter the weight update rule in the equation given here. What is the weight update rule? Wi equal to Wi plus delta Wi, a small change to the Wi, that is delta Wi. That will give your new weight adjusted new weight, right? In the algorithm, in this algorithm, we can make a small, in this equation, we can make a small update. We can make a small change by making the weight update on the nth iteration it depends partially on the update that occurred during the n-1th iteration as follows. Means the weight adjustment that you do in nth iteration depends on the update that happened in n-1th iteration, that is its previous iteration. How is it done? Delta Wji, here no longer you have W1, W2, W3, that is Wi. You have Wji because you have some weight associated when one input from unit I is being fed to unit J. Okay, you have some weight associated with it. That weight is called as Wji. When you are feeding some output from unit I to unit J, If there is some weight associated with this, that is represented as Wji. Okay, so the change to that weight Wji in the nth iteration, how do you denote that? How do you calculate that weight? This is your normal grade weight adjustment rule. You know that, right? Learning rate multiplied by the prediction error at the unit j. Unit j has some prediction error which is dependent on this weight. Did you understand now? This is what I tried to make it clear in the previous explanation. When some input unit is feeding its output to output unit j, in that case there will be some error associated with that, represented as Wji. Now what is the prediction error delta in with this output unit j, associated with this output unit j, depends on this Wji, right? That is why you are using, in order to adjust this weight Wji, you are using this prediction error delta j, and the input that is fed from I to j. Okay, that gives your learning rule. Remember, it is same as your new T minus OXI, which you learned in your perceptron training rule. Do not get confused. Same thing. You are giving some index numbers here because lots of layers are there. Okay, so it is new delta j xji plus, you are also considering the weight in your previous iteration, weight adjustment made in your previous iteration. What is that weight adjustment? Delta Wji made in the previous iteration n minus 1. That has effect on the weight adjustment that is going to be done in this current iteration, that is n. Previous iteration n minus 1. What is the weight adjustment done? That has some impact on this current iteration n's weight adjustment Wji. Delta Wji. Got it? Now, did you see one term? Already we are frustrated with so many terms, and again a new term is coming into picture here. But actually it does some important work for us. So I accept it. Students, this is the last term I am going to add for your mathematical models. Okay, do not worry. No more terms I'll introduce further. Okay, so be tolerant with this alpha term also. What is this alpha term that is being introduced here? In order to consider the previous iterations weight adjustment, to calculate current iterations weight adjustment, we are also associating some alpha term here. This is called as the momentum. This alpha term is called as the momentum. Let me explain this equation more clearly for you. I think it will be easy then. Here, delta Wji of n is the weight update performed during the nth iteration through the main loop of the algorithm. Okay, and this alpha what we are using lies between 0 and 1. That is a constant term called the momentum. Okay, now before going to this, let us assume a ball, say this is the mountain slope. A ball started rolling down. Okay, how do you understand about the momentum of that ball? Momentum is, in physics, what is the formula for momentum? Mass into velocity, you remember? So the mass and its the velocity and its associated mass will determine the momentum of a ball rolling down a hill. Now, if the mass is more, velocity also will be increased, right? Momentum will be increased, because if you roll a heavier rock from down the hill, it will roll faster than rolling a small ball down the hill. Did you notice that? Common sense, right? You have a hill like mountain slope like this. You roll a big rock down the hill. The mass is very high. So it increases the momentum. It increases the speed of it rolling down the hill. But if you take a small ball and start rolling down the hill, what will happen? Because the mass is very less, even the momentum will be less. It will slowly roll down the hill. Okay. Why I am taking this example is the model is trying to reach the global minimum. How fast it converges to this minimum point, that is determined by alpha, momentum. Okay. Now let us study about this further. Notice the first term on the right of this equation is just the weight update rule in the backpropagation algorithm. This you need not worry, you know about that very clearly. Learning rate into prediction error into the input term will give you the weight adjustment. But here you are also considering previous iteration's weight adjustment and multiplied by a constant term alpha called as momentum. Now the second term on the right is new term we are adding here, which is called as the momentum term. This entire term is called as the momentum term. To see the effect of this momentum term, consider that the gradient descent search trajectory is analogous to that of a ball rolling down the error surface. This is our error surface. Initially, the error will be very high. Slowly, it rolls down. Slowly, the model learns better and better, and it reaches a point, the foot of the mountain, the minimum point of the error surface, where the prediction error is very low, almost accurate predictions it can make at this point, right? To see this effect of this momentum term, consider that the gradient descent search trajectory is analogous to that of a ball rolling down the error surface. But here we are considering it as a momentumless ball, means it is rolling constantly without any speeding in its velocity. Okay. Now the effect of alpha is to add momentum that tends to keep the ball rolling in the same direction from one iteration to the next iteration. So alpha can be considered as the momentum you provide to the to keep the to keep the ball rolling. Why? Because say if there is a flat surface, the ball will come here and it will stop, it will not roll further, right? So it requires some momentum. Why it has stopped here? Listen carefully. Initially the ball started rolling down, there is a flat surface here, it has stopped here, means there is a local minimum. The prediction error is being reduced when it has reached a local minimum. It tends to stop there, adjusting with the local minimum, but actual destination is this, the global minimum. Minimum prediction error is here, not here, but local best prediction is made here. That is why the ball may stop here with the local prediction by adjusting with the local prediction, but by adjusting with this local reduced prediction error, but that is not the global minimum, right? It should not stop there. So provide it a push, provide it a momentum so that it starts reducing its error further to reach its final global minimum. That momentum is called as this alpha. You are providing the momentum to the model so that it doesn't adjust with its local minimum but proceeds forward to the global minimum. Got it? The effect of alpha is to add momentum that tends to keep the ball rolling. It should not adjust somewhere in between. In the same direction, in this direction, from one iteration to the next iteration. Why one iteration to next iteration? In one iteration, some weight adjustment is done. In the next iteration, some weight adjustment is done. Now, when adjusting this weight, consider this constant term alpha so that it doesn't adjust with the local minimum but proceed towards the global minimum. This can sometimes have the effect of keeping the ball rolling, continuously rolling through small local minima. What I said, it should not adjust with the local minima in the error surface or along the flat regions in the surface. What I told you, it should not adjust with some flat regions or with some local minima where the ball would stop if there were no momentum, right? It will settle here. It should not settle here. Provided momentum alpha so that it proceeds further to the global minimum, right? It also has the effect of gradually increasing the step size of the search in regions where the gradient is unchanging, thereby speeding the convergence. Gradient means what? Slope. Where the gradient is not changing, say it is a flat surface, there is no steepness in the inclination. In that case, it may adjust there. So in that case, it will provide it a speed. It will provide a momentum, it will provide a push to the model in order to go further. Don't stop here, go further, because you may reach a global minimum where the prediction error is very, very low, which is your optimal adjustment of weights that have to be reached by the model. Now, learning in arbitrary acyclic networks, how it is performed. The definition of backpropagation presented applies only to two-layer networks. But irrespective of this, it has been found that in practical applications, backpropagation algorithm, though it works with two layers, it works very, very well. Okay, but what is the drawback of this is it actually applies to this backpropagation algorithm applies to only two layers of the network. The algorithm given easily generalizes to feed forward networks of arbitrary depth. But same algorithm, backpropagation algorithm, though it is applying only for two-layer networks, this can be generalized. This can be applied with little modifications to feed forward networks with arbitrary depth. Arbitrary means changing depth. You may have 2 layers, 3 layers, 4 layers, 5 layers. How much ever the neural network becomes complex, still this backpropagation algorithm can be taken as a basis and perform some modifications to that backpropagation algorithm and apply it to any number of leveled feed forward networks. The weight update rule is retained, and the only change is to the processor of computing this delta values, that is the error measure. Initially, how it is calculated in backpropagation, error measure is given back as input to the input layer in order to adjust the weights. But because it is feed forward network, how the delta has to be calculated, how the error have to be calculated, some adjustment have to be done, some modification have to be done, so that it works with feed forward networks also, not only with backpropagation models. In general, delta R value for a unit R in layer M. Did you understand? Say this is my layer M. This may be my unit R in that layer M. That is how I denote. Okay. In general, the delta R value for a unit in layer M, say this gives a prediction error delta. It is computed from the delta values at the next deeper layer M+1 according to this particular step, what we have given here. This step may be repeated for any number of hidden layers in the network. For each unit in the layer, see how the prediction is calculated. Prediction error is calculated. Now that applies to all the layers. Okay, so at this particular unit in the layer M, at this particular unit in the layer M, how the prediction error is calculated according to this formula what is given. Right, delta R equal to OR multiplied by 1 minus OR, that is your prediction error at unit R, and summing up all the layers, weights and its predictions, right? Now that is what we have given here. It is equally straightforward to generalize the algorithm to any directed acyclic graph, regardless of whether the network units are arranged in uniform layers or not. Whether the network is arranged in uniform layers, proceeding in a particular direction, or whether one layer is larger, one layer is smaller. There is non-linear arrangement of the units in the neural network. Still, so far, we can use the algorithm that is given in backpropagation. In the case that they are not, means if they are not able to be arranged in uniform layers, in that case, the rule for calculating the prediction error delta for any internal unit is you can make a little change. See, here we are given with the formula. For that formula, we can make a little change. What is the change we are making? Instead of using here the layers, we use downstream R. Downstream R means whatever layer are coming after this unit R, not before this unit R. That is called as downstream. Say if you have some layer like this, and if you have some layer like this and some more unit like this, then these two layers are downstream to this layer because they occur later in the network, right? So in the case that they are not, means we can't arrange them in uniform layers, the rule for calculating the prediction error delta for any internal unit, that is any unit that is not an output unit, means input unit and output unit you have as boundary layers, but anywhere if you want to calculate the error in between, how it is calculated? Delta R, the prediction error associated with the unit R, is calculated as the prediction error associated with it into 1 minus prediction error associated with that unit R, multiplied by sum up all the weights of a particular layer occurring downstream of this R, occurring later to this unit R. Take all those weights of that particular layer with respect to the unit R, calculate that layer's prediction error. Okay, this is how you need to calculate the prediction error at a particular unit R, where downstream R is the set of units immediately downstream from unit R. As I said, say if you have R here, this is the layer occurring downstream. If you have R here, this is the layer occurring in the downstream. Okay, after that particular unit, where downstream R is the set of units immediately downstream from unit R in the network, that is all units whose inputs include the output of unit R. Say this is your unit R. Now all the outputs of unit R is occurring as inputs to the next layer. That is why we call them as downstream to this in unit R. Okay, in that case we calculate the prediction error associated with that unit R as according to this example, according to this formula. Okay, this is how we complete our neural networks chapter. Let us just quickly summarize what we have learned. We got the introduction to neural networks by understanding the biological motivation a human brain provides to neural networks, and the neural network representation by taking autonomous driving vehicle by that system called as Alvin. And we have also seen that what are the appropriate problems for neural network learning, say where the noise is too much in the data, and where the data is in the form of attribute value pairs, or when the data is say taking too much time, if the model can adjust with too much of learning time, but where quick evaluation is required. In that cases you have to 5 minutes. Last. I think. Okay, so where the noise is more, where the learning time can be more, but the evaluation time should be lesser, and where attribute value pairs can be given as input. In all these cases, you can choose neural networks, and where internal interpretation is not required. See, decision trees, internal interpretation is very clear, but with neural networks, you can't interpret that clear, right? So in such cases, you can opt for this neural network learning. And we have also understood how perceptrons can be used to represent various Boolean expressions, and the perceptron training rule, and the gradient descent and the delta rule. How perceptron training rule is sufficient for linearly separable problems, whereas gradient descent and the delta rule should be used for non-linearly separable problems. And multi-layer networks and the backpropagation algorithm, we have covered it today. By using sigmoid function, how you can smooth the data, how you can smooth the output that is given by the perceptron. All this we have covered in today's class. Now, can you quickly answer what is the output range of a sigmoid function, students? It is -1 + 1 or 0 and 1? It is 0 and 1. We have to smooth the values so that it doesn't fix with a specific threshold, and it can lie anywhere between 0 and 1. In order to do that, we opt for this sigmoid function in neural networks so that its range falls between 0 and 1. Sigmoid function can also be called as, very good, logistic function
Logistic
or
function.
logistic. Normally we call it as logistic, but general usage is logistic function. How is sigmoid unit represented?
One by one
Very
plus
good.
e power
1 by
minus x.
1 plus e power minus x, and it looks like a S curve. Okay. Okay. Sorry for taking too much of your time. In order to complete the syllabus, the third chapter, I have taken this time. Yeah, we'll meet in the next class with fourth module.